Okay, good afternoon all. I hope I'm audible. Uh, we are going to learn how generative models can be used for the anomaly detection purpose. On day 3, we discussed about two generative models. One is autoencoder and then a GAN network. And today we have discussed a diffusion model. And all these models we discuss from the perspective of generating some synthetic data. Okay. Whereas now these models can be twisted to perform
ऐसा कुछ नहीं सोच
something
सकता है
called
इंडियन
as anomaly detection.
वाला नहीं है डायरेक्ट
Yeah.
ट्यूसडे को होगा फिर वो
हिट जाएगा मतलब
फिर उसका ओपीडी रहता ना मंडे
Ketan, you have any query?
और बाकी दिन का वो सब डिलीवरी करता है देखते भाई जाना तो पड़ेगा
Ketan, just mute yourself. Okay, so we will use these generative models for the purpose of anomaly detection. Okay, so let's try to understand what is anomaly first. And again, here before that, let me give you the brief about the details about this course. So here also we'll be having 3 chapters, and same problem we will be trying to solve using first of all classical supervised machine learning technique, that is XGBoost. I'll not highlight this particular approach much, but at least we will go through the chapter and we will try to understand problem statement and how we are going to perform this anomaly detection task. Then we will use autoencoder to perform the same task, anomaly detection, and GANs again, right? And finally, based on these 3 chapters, you have an assessment that is again separate chapter where you have to solve similar problem and you have to uh, achieve maximum accuracy. And based on your submission, again, you'll be awarded with a certificate here also. Okay. So first of all, let's try to understand what is anomaly and problem statement. So I'm using this presentation. Again, you can find it on the same page, right? So where the start button is there, above that, you will see a PowerPoint presentation. Okay. So now you must be familiar with so far supervised, unsupervised learning, then autoencoders and GAN architecture. We have discussed in detail with simple hands-on as well. Okay, so let's try to define anomaly. Okay, anomaly means a data point which differs significantly from the other data points that set. For example, if you observe here, all the white sheeps are there, and there is a suddenly black sheep appearing here. So it is not following the pattern of nearby data points, right? Or all the data points that we have, and that we called as an anomaly. Okay. So this is just a simple case that we are discussing, right? We don't have any significant real life application, but at least you got the idea what is anomaly. Now, this is an observation that is likely generated by a different mechanism. For example, you are recording, let's say, a salary of the employee, right? And by mistake, in the salary column, instead of maintaining the salary, you just mentioned the, let's say, phone number or age of the person. So that is not going to follow the typical pattern that we have in the salary column. Okay. So maybe for few employees, salary could be in 10 digits, but obviously for most of the employees, the salary may be in the 5 to 6 digits, right? But at that place, you are mentioning the, let's say, age or maybe the phone number. So that is not going to follow the salary of other employees in that column. Okay. Similarly, the real life application can be in the finance domain where you have credit card transactions and typically you, let's say, perform around spend around 20 to 30,000 per month using that credit card. But suddenly on one day, there are 3-4 transactions are happening, and Aryan, are you there?
Sir, some new participants are joining, that's why they are not.
I'm just trying to change the privilege here. Uh, Aryan, Kunal,
Sir, I am here.
you just try to change the privilege for the participant. They should not be able to unmute by themselves.
Yes, sir, yes. Okay, sir.
Okay, we will open that. Okay, so here we are saying the credit card transactions where typically you're spending 20, 30,000, but suddenly let's say transactions of 1 lakh are happening. So it is going to be normal pattern in your transactions, and immediately credit card company is going to contact you to verify whether the transactions made by you or not. Okay. So likewise, many such applications are there in healthcare, right? So if you'll see all the normal patients reports follow some pattern, and suddenly for abnormal patient, you'll see the uh, pathological reports are going to give you some odd values. Okay, so in that case also we can treat it as anomaly. So likewise, we have all these applications and where it is important to find out the anomaly in the data set. Okay, which could lead to maybe financial loss, or maybe it is can cause death to a person, or maybe you'll be having some sort of any other kind of loss, right? So in order to avoid that, we have to find out this abnormal pattern in our data set. Okay. Now, if you see, there are two pictures here, and can you tell me, is there any difference in these two pictures, except the, I can say, height of these Mona Lisa? Okay, forget about this part, and this is slightly, shifted downward. So apart from this, do you find any other difference in these pictures? Yeah, it looks same, right? So almost there is no difference. But if you see here, if you focus with this, here river is appearing, right? It is a bit brighter, but here it is darker, right? So it is not appearing here. So point here is there will be some scenarios where it is not that easy to find out the difference in the pattern. Okay, for the naked eye. So imagine you have hundreds and millions of let's say financial transactions, and you need to identify which transaction is not following the normal pattern. So in that case, you can see it is important for us to identify those sort of abnormalities of AI technique. Okay. Now, these are the some of the applications we'll be having in which anomaly detection is important. Let's try to understand one of the case study here, and how it is important to identify that anomaly. For example, there was SCADA systems where only a 500 kilobyte computer worm that targeted those SCADA systems, and that was spread through the USB flash drives. Okay, you can refer to that case study by clicking on that. But here, uh, it analyzed and targeted Windows network and computer systems, right? And as a result, it infected over 1 lakh computers and 22 manufacturing sites, right? And because of which it impacted a nuclear facility, destroying 984 uranium enriching centrifuges. Okay, so you can see a simple 500 kilobyte worm is going to affect and cause this much of loss. And it's very important in such application to identify the worms or the phishing attacks or breach of your system, etc. Now, let's try to understand which problem statement we are going to solve using these AI technique here. First, the problem is intrusion detection data set we have, right? So where we'll be having network packet logs with us. So to a system, normal network packet logs are there, and it also has some sort of intrusion happened in the past, that abnormality is also present in the data set, and we want to detect those using the machine learning model, supervised and unsupervised model. So if you want, you can refer to this data set on this link. And right now, it is not necessary to get domain knowledge from that data set. For example, if you're not much aware about the security terms and the network packet terms, right? So don't worry about it. Our job is to just take this data set and try to identify anomaly by following the AI models. Okay. These are the details about the data set. So total size of data set is 743 megabytes. The number of features or columns present in the data set are 31. So out of which 22 are numerical and 9 are categorical. Right. So we have tabular data set that indicates we have 31 columns or features are there, and number of rows are 18 million. Okay, 18 into 10 to the power 6. These many rows are there. And finally, we'll be having a label column also. Okay, this is called as label. Right? And label can belong to one of the 23 categories. So it is a multi-class classification. So it can have 23 categories. Right? So it is a multi-class classification. Now, our goal is to be observing all these patterns in the data set and corresponding labels. And we want to detect the anomalies in the network packet logs. Okay, that is the brief about the data set. Now, these are a few further details about these features. So some of them are basic features like duration of that, then source byte transfer, destination bytes, etc. Then some content features are there, and some traffic features are there. And the green indicates the numerical features, and this gray indicates the categorical features. So some features are numerical and some features are categorical. Okay. Again, I'm saying you don't have to go and investigate all these meaning of all these features, right? We'll just try to understand how these GANs and autoencoders are used in order to find out, in general, abnormality in the data set. Fine? Fine. So this is just again further visualization of the data set. Now, these are the some blogs published around 2017, and some newspaper, they have mentioned that what are the impacts of these sort of attacks. And if you observe here, there is almost 38 billion telecom fraud happened, and out of which $12 billion are using network or IP fraud. That means 1/3 of the attacks are happened because of this network and IP fraud. Okay, so that's why we are focusing on this type of problem statement where network packet logs we can observe, and based on that we can identify the abnormalities or the attacks in the system. Okay, and to do that, we have three models. One is XGBoost, which is a supervised model. That means it is basically based on your labels also. And we have unsupervised models. One is autoencoder and GANs. And we have seen why they are being called as unsupervised models. Okay. So we'll see one by one how these models are going to solve the problem. Now, question is why we want to use this XGBoost. First of all, it is based on decision trees, right? And combination of boosting and decision trees here. And it is one of the most popular model in machine learning where we want to perform classification or regression. Though it is slightly computationally heavy, but still in terms of accuracy compared to other models, most of the time these boosted decision trees will win over all the remaining models. Okay. And so let me quickly just walk you through this how gradient boosted decision trees works. First of all, we'll take the data set, we'll train, and we will create a shallow tree here, right in the first layer. And then we will pass the test data set for that shallow tree, and it is going to give some error, and that we call it as a residual. And again, on that residual, we will train another decision tree, and again, we'll get some errors. and likewise we'll get again pass those errors or residuals to another tree and so on. And finally, based on these n number of trees, if you move gradually from left to right here, so you'll see that the residual or the error from subsequent trees are going to reduce, and there will be a point where error or residual is not going to reduce further, then we are going to stop. Okay. So this is how the boosted decision trees works. And this is one example of XGBoost. Here we have on x-axis drug dosage that is defined, and on y-axis the effectiveness of drug is mentioned. With respect to this example, we will just try to understand in a short how this XGBoost works, right? Again, it is not, I'm not going to introduce entire mathematics behind this XGBoost. Okay, just quickly to make you familiar and how this supervised model is going to help us to solve and what are its limitations we'll try to understand. So here, as you can see, drug dosage is very low, then effectiveness is low. And if drug dosage is increasing here, so effectiveness is increasing. And beyond some point, the drug dosage is increased, then its effectiveness is dropping here. So that means here, if the drug dosage is somewhere in here in the range 20, then it is good, or below that also it is not going to be effective, and above that also it is going to be not effective. Okay. Now, in case of this XGBoost reconstruction, we'll start with a single leaf where we will place all the residuals. Okay, so we will start with a line here, horizontal line, and we'll say this is the relationship between drug dosage and effectiveness. And obviously, you can see it is a kind of a random line. It is not, having any sort of mapping relationship between drug dosage and effectiveness. But with respect to this line, we'll get some residuals. So if you see for this point, we have minus 10.5 as a residual. For this point, we have 6.5 residual. For this point, we have 7.5. And for this point, we are going to have minus 7.5. Okay. So that is how far these points are away from this considered line. And this is the residual we get, and we are going to place it in a single node of the tree. Now, for this particular single node, we are going to calculate the similarity score. Just to we have to calculate the information gain further. So for that reason, we are going to first calculate similarity score here based on the residuals. So what we do, we will take sum of residuals squared and the number of residuals divided by and plus regularizations. And as of now, let's say regularization is 0. For overfit and underfit control, we'll be using that regularization parameter. This will give me a similarity score. And if I do that math, so I'll get similarity score for this node is going to be 4. So these terms are going to cancel out, and minus 10.5 plus 6.5, it will give you 4, and 4 square divided by 4 will give you 4 here. Okay. So this is similarity score for the node. And now what we'll do, we will try to divide these this node into two parts. On left, first of all, we'll place only one data point, and in the right hand side of the tree, we'll place all the remaining 3 points. Okay, so we'll place the residual minus 10.5 to the left and remaining 3 points to the right. Again, we'll calculate similarity score using the previous formula for the left tree as well as for the right tree. And then based on similarity score of root, the left child and right child, we will try to calculate something called as gain. And we want to make these partitions in a such a way that the gain will be maximized. So if I do this partition, I'm getting the left similarity plus right similarity minus root similarity. That is a gain formula. And here I'm getting 120, 10, here 14, and here we have 4. And if I do that math, I'll get gain for this sort of partition is 120.33. Okay. Likewise, I will calculate the gain for another type of distribution. So right now 1 point to the left and 3 points to the right. So what I'll do now, I'll place 2 points to the left and 2 points to the right. And now you can see here based on that, if drug dosage is less than 22.5, we'll be having these residuals, and greater than that, we'll be having these residuals. Again, we'll calculate similarity score for this root, left child and right child. and we'll calculate information gain using this formula. And we are getting information gain in this case equal to 4. Okay. Now this information gain for this partition is lesser than the previous partition. And obviously, now we will treat this partition is better for the splitting of your data compared to the second partition. Likewise, we'll also check the third partition where 3 points to the left and 1 point to the right, and we'll calculate information gain. And it is a 56.33, which is again fairly lower than the first information gain. Okay, so that means out of these 3 partitions, the first partition is giving you maximum information gain. Okay, so 1 point to the left and 3 points to the right. Now again, for remaining these 3 points, we'll try to perform the splitting by making 1 point to the right here, that is 6.5, and 2 points to the right here. Again, I will calculate here similarity score for the left and right child and information gain. So it is 28.17. So likewise, we'll do again 2 points to the left and 1 point to the right and calculate information gain. And likewise, we'll perform the construct the tree here. Now, once the tree is constructed, we want to perform the prediction. So what we'll do, we will consider any data point. Based on these values, we'll place it to the left or right. And according to, we will perform the prediction of the effectiveness, right? And once we get the prediction, we'll again calculate the residuals. Sorry. Okay. So again, we will get those residuals. How to remove this? Okay. So again, we'll get the residuals, right? Now for this, again, we'll construct a new decision tree, right? So likewise, we'll proceed for the next tree. Again, we'll get some residuals. Again, we'll go to the next tree and so on. And when we go on constructing the new trees, the residuals start decreasing. So if you observe compared to the previous residuals, right? So where minus 10.5, 6.5, 7.5 was there. So it is reduced. Okay. And likewise, we'll construct the go on constructing trees, and finally we'll be having a XGBoost model here. Okay. Now question is why decision trees, sorry, this XGBoost? Because if you see the tree-based models, we have these decision trees are there, random forest is there, GBDT is there, and XGBoost is there. And out of which XGBoost is the optimized version, which is very accurate compared to remaining other tree-based algorithms. Okay, and they have tried to see why this XGBoost is going to always perform well with respect to multiple examples here, right? So they have tested this XGBoost model and remaining machine learning models on 165 machine learning data sets on different domains. And they found that um, almost every time the rank of this XGBoost is on top 3. Okay, so there will be sometimes one of the model is going to outperform the decision tree, but XGBoost was always in the top 3 ranks. Okay, and that's why we are going to pick this decision tree. And also this XGBoost can be parallelized using on GPU using this package called as a rapid suit, right? In this rapid suit, we have a CUML library, which is analogous to your scikit-learn library, where machine learning models can be trained and constructed. So CUML is uh, kind of GPU version or parallel version of scikit-learn, where all the models can be automatically trained on the GPU side. Okay, so that ultimately they will run faster. Fine. So now here you will see that rapids, when we use it, is going to run very fast the training, and we are going to perform this uh, anomaly detection task here. So what we'll do now, I'll try to just give you first of all idea about how to proceed throughout this course and what are the pre-processing and these techniques are applied here. And then I'll give you some time to work on this chapter around 5 to 10 minutes. Then you complete it and then we'll move to the next chapter. So this is the first chapter we have, and initially they have explained about the data sets. So if you are interested, you can go through these details. Okay, but as of now, let me quickly give you idea about this data set and all. So we are going to read this data set from the CSV file and create a data frame, and we are going to assign these column names. Okay, and they have already provided us these column names, right? So we don't have to change anything of that. And if you print the first 5 data points here, so the data set looks like this, right? So first data points are there, and these are the column names: duration, protocol type, service, flags, etc. Likewise, we'll be having these 41 independent variables and one dependent variable. So we'll be having 41 features and one dependent variable, that is label. Okay, so 41 plus 1, that is 42 columns are there in this data frame, and we'll see how many rows are there. Okay, so here we are going to see unique labels here. So with respect to this Smurf category, how many labels we'll be having? So 2 million. Okay, so 2.8 million or 28 lakh data points are belong to Smurf category. Then 10 lakh points belong to Neptune category, and here you can see 9 lakh points approximately belong to normal category. That means in the data set, overall we'll be having 9 lakh points approximately related to normal category, and remaining around 40 lakh data points related to abnormal category. So all the remaining categories are abnormal here. Okay, and only one category we have normal. Right. So as I mentioned, it is going to be multi-class classification. So we will be having these many classes here. And slightly, odd to notice here that uh, typically when we try to, capture the data in finance or healthcare domain, so normal data points are less. Sorry, normal data points are more, and abnormal data points are less. But reverse is happening here. So we have more abnormalities in our data set, right? So these many, if you do that sum, so around 35 lakh data points will be related to abnormal category, and 9 lakh related to a normal category. Okay, but anyways, it is not going to affect our model. So we will see. Now, as we know, these are the labels that we have, which are in the text format. So we have to convert into numerical format, and we have label encoder that is going to convert them into labels. Okay, and the numerical labels, right? Because while performing forward and backward propagation or the optimization of these models, then we have to perform the numerical operations. And in order to do that, we must have these labels in terms of numerical values. Okay. Then we will perform for categorical features one hot encoding, because the categorical features also have some text information here. For example, if I consider protocol type, it is having text information, TCP, UDP, and so on. The service is HTTP, FTP, whatever is there. Flags are also in text format. So we cannot process these data in text form in the model for training calculations. So we have to convert them into numerical, and to convert them into numerical, we are using one hot encoding here. Okay. So this is just to pre-process your data and make the total data set ready for training. So we have approximately 48 lakh in entries. That is the number of rows in the categorical data, and 48 lakh, so 34 columns in the numerical data. And combinedly, we'll be having 48 lakh data points and 122 columns here now after one hot encoding. Okay. So now we are going to perform the data splitting here into X10, X-test, Y10, and Y-test. So the entire data, where 25% we are going to consider into the test size. And if you see, finally, the data shape size, so we'll be having 36 lakh data points in the training and 12 lakh into the testing. Okay, we'll create this dictionary in order to load it on the further. So we are going to store that the pre-processed data, right, with their labels and the values into this dictionary here. Fine. So now let's start with our designing our model. So we are going to create first of our binary classifier. So what we'll do, rather than start with the multi-class classification, we will simply treat this data as a binary classifier. So we will be considering this, let's say, as a label 0, and for all the remaining labels, we will give them as 1. Okay, so rather than very specific category of abnormality, we'll say 0 stands for normal data, pointless label, and we will, wherever there is a Smurf, Neptune, and all these labels are there, we'll mention there 1. So now the problem becomes binary classification problem. And we will use this XGBoost model here to perform this binary classification. Okay, so this convert label to binary is going to take all the labels, and if it is not normal or abnormal, then we are going to label it as a 1. And if it is a normal, we are going to label it as 0. Okay, and that is how it is going to convert. And total number of anomalies that the training data set we have 29 lakh and 9 lakh in the test. Okay. So to train this XGBoost model, first of all, we have to define some parameters related to XGBoost. So objective is going to be whether it is going to be binary classification or multi-class classification. If it is a binary classification, we have to specify objective as a binary logistic. And if it is a multi-class, we have to mention, I think, soft probability. Okay, because softmax function will be used over there. Now, number of rounds is how many iterations we are going, maximum depth of the trees, maximum number of leaves of the trees. Okay, all these parameters are mentioned here. And one more parameter we have is number of GPUs. The current instance of the GPU that you got is having only one GPU. So number of GPUs are 1. And this is GPU hist method we have to specify explicitly to tell that the training is supposed to happen on the GPU side. Okay. So we will have these models now. Okay. So this, first of all, your xtrain and xtest are in data frame format. We have to convert them into a compatible format for XGBoost model. So that format is D matrix format. So we have to pass these xtrain and xtest and corresponding labels as binary ytrain and binary ytest. Okay. And just like that, we are going to start training this model, and you can see how fast the training is going to happen. So it took less than 1 second of time to complete the training with 9 iterations. And consistently, you can see the loss was dropping here. And that is a positive sign that your model is getting trained. Okay. So here, now you can see using this NVIDIA SMI command, you can get the details about the GPU. So right now we are not using the GPU, so it is showing 0% utilization. But once the training is happened, we transfer the data on the GPU side, and we have 22 GB of RAM, out of which 2 GB is used for this particular problem statement. Okay. Now with this, we can perform the classification. So I can simply specify that if the probability score is greater than 0.5, we'll assign it to 1, that is anomaly, and less than 0.5, we'll assign it to the normal. Okay. And based on that, if you do that sum, you are getting these many points will be considered as abnormal. Okay, that is anomaly. And for 0, we don't have any addition, so we just keep that. And if I try to draw this area under curve, it is giving me almost 1. That indicates your accuracy is almost 100%. And you can print that accuracy also. You can see it is 99.97 accuracy. Right. So this binary classifier is working perfectly fine. Then you can verify it using the confusion matrix also. So these are we have discussed this confusion matrix, how to read. Here we can see the diagonal entries are having maximum values, right? Whereas non-diagonals are minimum. So non-diagonal entries are showing misclassification, and diagonal entries show the correct classifications. Fine. So you can verify that AUC, you can visualize also. So you can see it is area under curve is going to be 1 here. Right. And this XGB is also having a feature of it is going to give you feature importance, right? So out of all these features, so it is showing that source bytes are most important, right? And then next is the destination host difference rate will be the second most. And likewise, in the descending order, it has displayed which features are most important in order to perform those classifications, right? Now, what if we'll be having more anomalies and the no, than the normal, sorry, less anomalies than the normal data, right? So in earlier case, we had more data points where they belong to abnormal category and less data points related to normal category. So we'll do the reverse now. How to do that? So what we'll do, rather than taking all the anomalies from the data set, we'll take only 1% of anomalies, right? So if you take the less number of anomalies and now more data points related normal, right? So you can see now normal data points are around 9 lakh and abnormal data points are around, let's say, 10,000, right? So let's try to see whether this model will work fine or not. And now at this point, you have to go back and execute all these cells since beginning, and you need to observe whether there is any change in the accuracy or not. And you will realize that accuracy will remain same. So this XGBoost is going to work fine for both cases where normal data points are more, abnormal are less, or vice versa. Okay, fine. So this is about the binary classification. Now they're asking you for the as an exercise for to solve it for multi-class classification, right? And now you can see here they're changing those parameters. So objective function earlier was a binary logistic, but it is now multi-soft probe because you have multiple categories, and number of classes is changed to number of labels, right? And number of labels is also encoded using shown here. It is how many we have, right? So these are all the parameters that we have now for multi-class classification, and they're asking you to modify this code. Okay, so as of now, I'll just copy paste the same code that we used earlier, and we'll try to modify it. So here, only difference is now we don't have to use binary labels because it is multi-class. So we have to use the white train and white test as it is, right? So we don't want to use binary labels. Okay, and finally, we will just start this model training. Okay, fine. So I'll remove this now, and I will train this model. Slightly, it will take more time because now you can see we have multi-class classification, but still it is taking around 2 seconds compared to the previous case. Okay, so now let's predict and we'll see the accuracy of this model. So again, it is 99.98% accuracy. And in confusion matrix also, you can see the diagonal entries are going to be with the maximum values and non-diagonal entries are minimum, right? So the same model is working for your multi-class classification also. Fine. Okay. So now we'll
Sorry,
take.
can you go back to the place where you could record the model? 4.1, I believe.
4 point.
4.1 or just yeah, where you defined the model. Yeah.
Yeah.
XGB. Yeah.
Yeah, I think you might also find solution for that somewhere. Is it not? I think. No, I don't think there is solution. So what I just changed here, earlier we used binary labels here because we tried to train our binary classifier, but now I'm using original labels. So where multi-class labels are there. So that is the only change I made here.
Okay. Sure. Thank you, sir.
Yeah, fine. You now go on. I'll give you 15 minutes time. So since beginning, you read the instructions and step by step you execute. And advice is not to investigate too much about this domain specific knowledge here. Right? We are just caring about whether these models are capable of identifying the normal data points and abnormality or not. Okay, fine. So try it. And meanwhile, if you have any questions, you please drop in the chat box or open your mic and let's have a discussion. Yes, there is a question related to even the data set is imbalanced, still the XGBoost is performing well, right? So that is the beauty of this model. So in case of anomaly detection, generally you will be having data which is fairly imbalanced, and still that is the case. You can see the model is working perfect. Okay, and it's not only the accuracy. You can verify using the confusion matrix also. For all the classes, you are getting better accuracy, not only for a large number of data points, right? So in every category, you can see diagonally here, 3,000 data points are correctly classified and only 22 are misclassified, right? Likewise here, even though we have almost 26, sorry, 2,68,000 and only 25 are getting misclassified. Okay. If your code is not running, just make sure here you can see the instance is launched and the timeline is showing here. And if problem still persists, you try to refresh this page first. You close this window, Jupyter Lab, and again try to launch it. Okay, that is second, try. And if still it is not working, stop the task and restart it. Okay, you may try the last option, stop and restart it. Hopefully it will work out. And if still it is, let's say, not working, then if you're connected through your institute Wi-Fi network, maybe it is blocking sometime. So you try to switch to your mobile hotspot and try. Okay. Otherwise, generally the errors don't occur. Rarely this happens, and it is your either systems problem or network problem. Okay, I hope all of you got the idea about the problem statement now, and this how XGBoost is perform classification on normal and anomalous data points. Okay, fine. So if you have completed this chapter, there is no assessment as such in this chapter, but at the end you can answer these questions. Okay, because answering question is also important. You need to in order to generate the final certificate, you need to answer these questions, because if you see in the, I think, a progress bar, it is going to tell you how much weightage for every assessment and the MCQ test. It will take bit time. Okay, meanwhile, let me stop this instance. Okay, so stop this first chapter instance, go to this network anomaly detection chapter, and using autoencoders, and try to start this cloud instance. Okay, for second chapter. And now you can see here in the progress bar, you have 70% weightage for the final assessment. And for lab 1, lab 2, lab 3, it is having 10%. So you have to also solve the MCQs that are mentioned below. Okay. So again, very simple MCQs are there. So autoencoder, you know that it is unsupervised learning. Which following data set you have gone through. So that is again the similar problem statement mentioned here. Okay, so let me explain the problem statement, or sorry, the model that we are going to use in the second chapter. So if you observe in the first notebook or chapter, we tried to solve the problem using supervised learning. Okay, so when you say supervised learning, you have features and corresponding labels. Okay, so if that is the case, it is very easy for us to find out whether this anomaly or not. But the problem is, when we go for supervised learning, in your training set, you must have all type of abnormal activities or anomalies present in the training data set itself. Otherwise, it will not have experience of that, right? So for example, we have 23 different types of attacks happen. So you must have the data points related to those 23 different types of attacks in your data set. You must have all these data points present in your data set. Now, even though let's say you manage to have, let's say, 23 different types of attacks happened so far, and you will have all that data, these data points in your data set. So when you train your model, right, you will get all these 23 attacks learning. Okay, the model will understand these are the 23 different types of attacks are happened. Now, when you find pass one of the 23 attacks through this model, so it will tell that it is anomaly. Okay, so it is looks very easy in this domain, but problem is that what's the guarantee that when new attack will happen, it will be of one of these category, right? So the hackers or the intruders are trying to be more innovative so that they can breach your system, right? So the now next time the attack is completely new and it is 24th new attack, and this attack information or the learning is not present in this model, because the model has learned on the previous history of these attacks, and model has no experience about the new type of attack. So obviously, if it is not belonging to one of these 23 categories, so it may be classified as a normal, right? So the thing is here, every time an hacker or attacker is going to try to breach your system, he or she is going to come up with a new approach. And the limitation of supervised learning is it can only learn what happened in the past, because whatever present in the data set, that only be learned. A new type of attack for which experience is not there in your training data set, so it may be classified as a normal, because model has never seen this type of new attack. Okay, so that's the limitation of supervised learning, right? And here the 24th attack is called as 0-day attack, right? That means it is completely new attack. Okay, now question is how to tackle this sort of new attacks, right? And to do that, will be using unsupervised learning. So here what we'll do, rather than trying our model to learn about these features and these labels, so what we'll do, we will tell that, okay, don't learn the relationship between feature and label. So you try to just understand how normal packet looks like. Okay, you just try to understand normal packets pattern, forget about the label, right? We will pass the normal data points to the model, and model has experience about the normal data points. Now, if anything is not following the normal data points, that will be categorized as anomaly, right? Maybe it is 23 categories, or any new category will be of the attack is going to happen. It will be categorized as anomaly, right? So here we are not going to, bind our model to have limited to this particular 23 attacks, but rather we will say, you just understand how normal packet looks like, right? And if something else other than normal is there, then we categorize as anomaly. Okay, and that is called as unsupervised, right? And this is going to tackle the problem of new attacks also, right? And that's why most of the time in this finance domain, we go with the unsupervised learning, right? So that we can ensure that any new type of attack will be there that can be handled also. Okay. Now, one of the model that we discussed on day 3, that is autoencoder, and we have seen in details how autoencoders are getting trained in that compression decompression model, and how the loss like mean squared error is back propagated, right? And typically for that mean squared error, we call it as a reconstruction loss also. Okay, so now we are going to solve the same problem using autoencoders. Okay, now I'll not go into the much details of autoencoder architecture and all, but let me try to give you idea how we are going to perform the same task using autoencoder, because we have used autoencoders in earlier case for the different purpose like image compression, decompression, image colorization, image denoising purpose. But now here we are going to use the same autoencoder for the purpose of anomaly detection, right? So first of all, the normal data pre-processing is going to happen, like, so all these data will be loaded, and we are going to again consider the percentage anomalies are 1%, right? Now here data is standardized, and now here we are creating these autoencoder model here. First of all, we'll create autoencoder. So here they have mentioned the input dimension will be the number of columns in the training data set here. So if you visualize this data now, we will be having this tabular data where we'll be having this number of features or columns, right? So features, and we'll be having this number of data points. Now input dimension, and the first dimension shape we are considering, that means number of columns in your data set, right? So this is my first data point, let's say x1. This is going to be the second data point, x2, in row wise, and so on. So we will take this x1 shape. One means how many features are there, right? So that vectors dimension we are taking. Okay. Then batch size we are considering 512. That means at a time we are going to feed 512 data points, and latent space or latent dimension is 4 here. Okay. So if you recall the latent dimension, it is just at the end of encoder part, how many neurons we are going to consider. Okay. So here at this point we are going to consider 4 neurons. That is the latent dimension. And the number of epochs for which we are going to train is going to be 10, right? So let's try to understand now this autoencoder architecture. So here, first of all, input data, we are going to take input here. Shape is going to be input dimension, that is number of features. Then we are going to create 96 neurons in the first layer, then 64 neurons in the second, then 48, 16, and so on. Okay, till you'll get 4. So in the first layer, we will be having 96 neurons. In second layer, we'll be having 64. Then we will be having 48. Then we will be having 16. Okay. And then finally, we'll be having 4. Okay. So this is your latent space dimension. This is your encoder. Now you can see here, this is how I designed your encoder. So this is our encoder part. Okay. You can see in every subsequent layer, number of neurons are getting reduced. And decoder is going to be exact mirror image of this. So 4, then we'll be having 16 neurons here, right? Then we'll be having 48 neurons, then 64, and finally 96. And then output dimension will be there, right? So this is your decoder part, right? So this is your decoder. This is encoder, and in between that, we have latent space. Right. So I hope you are able to recall the autoencoder architecture now. And input shape is input dimension. That is whatever the number of features are there. Okay. And this architecture block diagram is, coded here in this cell. Right. And now this model, first of all. Yeah. So you can see this is how your model looks like. And now they're asking you to design decoder part, right? So let me show you this decoder part. Let me erase this part here. Now you can observe how decoder part is going to be there. So they have just provided us code here, and they're asking you to fix the code, right? So you just need to mention here how many neurons to be there. And you can see the first layer in the decoder is going to have number of neurons equal to 16, right? 16. And here we have to connect the latent, this particular layer, right? Latent space layer. And latent space layer we have here is with the name encoder here. Sorry, latent encoding. Okay. So this latent encoding layer, we are going to connect to the decoder first layer. So that we have to specify here. Then after first layer, we'll be having 16, then we'll be having 48 neurons here in the second layer. Then decoder we have to attach here. Then again, after 48, there will be 64 neurons here. And again, we have to attach the decoder layer from the previous. And then we'll be having 96. And we will be having here decoder. And finally, we will be having this decoder attached to your output or the reconstructed data also. Okay, I hope it is clear. Right. So this is the neural network you have to design. And once you design the neural network, so we can combine them, and you can see the encoder, we started with 115, then 96, 64, 48, 16, then 4, then in reverse order 16, 48, then 64, 96, and 115. Okay, so this is how you have to first of all design the autoencoder architecture. Don't worry, I'll give you time for constructing that right in a while. But as of now, just pay attention how we are going to first of all design the network. And now coming to the point where we are going to train our model, right? And we know that in autoencoder, what we can do, the loss will be mean squared error, right? And we are going to monitor the accuracy of this model. And here you can see I'm passing xtrain and xtrain because I want whatever values I'm feeding as an input, I want the same values as to be generated by the decoder. So encoder is going to represent into lower dimension, maybe 115 dimension input is there. We are going to map into 4 dimension, and again we are going to reconstruct it to 115 dimension. Okay, and here, yeah, I think 2.3. Yeah, 2.3, we just created the opposite of the encoder, right? So what I want in case of decoder, I want 16 layers first, neurons first, then 48, 64, and 96, right? So that is what I placed here. So first of all, 60 neurons, then 48, 64, and 96, right? And we just need to attach the previous layers when we proceed further. So this is my one layer decoder created, and this decoder I have attached at the end here. Then I have created this decoder, and again I attach to the next. I created decoder and attached to the next. Okay. And for this decoder, the latent encoding need to be connected. So created here, right? And that making those connections. Okay. Now, when you, okay, the question is, why do we want to provide the name there is for decoder 1, 2, etc. So it is your choice, right? So name, you need to identify which layer you are talking about. So if you print their summary, so you need to say that if you it is saying, let's say only decoder, 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 so you will not be able to understand which decoder layer you are talking about, right? So you can give name anything here, right? So this decoder 1 means you are talking about the first layer in the decoder. Second decoder 2 means second layer of the decoder, and so on. Okay. And once you train this, you can see the accuracy you don't focus about right now. So loss is consistently dropping, right? So we care more about the mean squared error. And if you see that loss for training and test data set, it is consistently dropping and it got saturated after 8 epochs. So we'll stop at 10 here, right? So that is a positive sign that the loss is consistently dropping, right? Now question is, how we are going to perform the anomaly detection, right? So model is trained, we passed the training data set, which had 1% anomalies and 99% are the normal data points. Now question is, how we are going to perform the anomaly classification or detection, right? And idea is very, very simple. We just need to understand what is the reconstruction loss or mean squared error for normal data points and abnormal data points. So in our data set, most of the data points are 90% data points are okay. So what model will learn? How to, focus on the normal data points, compress them into lower dimension and reconstruct it. And mean squared error, it is supposed to be less. Okay, for that, right? And that mean squared error, we are going to call it as a reconstruction score, right? So what we'll do, first of all, we'll get the reconstruction score for the test data set. So once the model is trained, we'll pass the test data set for the prediction, and we'll get the reconstruction for every, and then we'll call it that mean squared error for all these data points, right? And we will add the reconstruction here score here. You can see the mean of reconstruction error is 0.004, okay, for all the data points. Now what we'll do, we will try to figure it out reconstruction error for both categories separately, right? So here I'm having the reconstruction scores, right? They are mentioned for some point. Many points here, you can see the reconstruction score is low in this range, right? So around 40,000 points here we have, right? So mean squared error is low, but there are few points where means reconstruction score is very high here. Okay, very few points are there. Reconstruction score is high. So what we'll do, we will try to group this reconstruction score for normal data points and abnormal, right? And if you observe the mean value for that label 0 is 0.004, and one normal data points you can see 0.005. Sorry, for anomaly points it is 0.005. Okay, so normal data score is mean square error is 0.0, but for anomaly data points the mean square error is 0.05. The reason is most of the data points are here in the data set that we have passed to this autoencoder were normal data points. And model has learned, because 99% data points are normal, so more obviously it will get biased to the normal data points, and it will try to minimize the mean squared error for those data points. And very few points were there which were anomaly, And for that, you can see the mean squared error is not reduced that much, and it is giving you mean squared error 0.05. Okay, so it is almost 10 times, okay, difference in the mean squared errors. And obviously, if normal data points have different values for MSC and abnormal data points have different, so it is clear indication that we are able to distinguish between the normal and abnormal points. Now, only thing is, how will you define that threshold value, right? So to define threshold value, you can come up with any your own logic. But what they have mentioned here, so they have said that we will take a true positive rate and false positive rate, and at what point it is getting the maximum value, right? And that is going to be our threshold. Okay, so threshold, optimal threshold is 0.03. So if that we get one of this method, other method is we can have a reconstruction, we'll take mean, then standard deviation, then reconstruction score plus 5 into standard deviation, and that will be statistical threshold. So you can use any of this, right? So one is giving 0.032, other is giving 0.0439. Okay, so you put that statistical threshold or any other threshold, and you try to plot the confusion matrix, and you can see now also you are with this autoencoder, you are getting this classification matrix here, and most of the data points are correctly classified with this logic also. Okay, so now you can see the same autoencoder, just by referring to this mean squared error, we are able to tell whether the point is anomaly or not. Okay, so point is there are here generative models are there, though we started the autoencoder use as a purpose for generating some information, but you can see how researchers try to use the same generative model but to solve the classical problem of anomaly detection. And only thing they have not changed the autoencoder architecture, they have not changed the loss function. Only thing, the way we are feeding the data to the model, and we are going to focus on that mean squared error, and based on some threshold logic, we are going to classify whether it is normal or anomaly. Fine. So this is how we are going to solve the problem of anomaly detection. Okay. So next is we have a multi-class classification. For that they have used, I think, k-means clustering, but that is not in the scope of our training, and it is not even required for the final assessment. So you can take this as an exercise, and after the training you can work on that. But for this session, just I'll give you a few minutes. Let's say 7 minutes. I'll give you to go through this chapter quickly and come to the final point where you are getting this accuracy. Okay. And again, if you have any questions, you can ask. I'll just solution for that decoder model is there. So in case you need, you can look at here. Right. Okay. So now work on that. Okay. Section 4. Yeah, section 4. Let me repeat one more time. So what we are doing, so we have normal data points and abnormal data points. Okay, so normal data points will be having 99% in our data set, right? And 1% data points are anomaly. Okay, now what will happen when we feed that data set to this autoencoder? So it will try to compress or low dimension representation of all the data points, and it will try to reconstruct it. And for the reconstruction, we have mean squared error, because the most of the data points are normal. So obviously your model will try to focus more on normal data points, how to represent in lower dimension and how to reconstruct them, right? So in that process, the mean squared error for the normal data point will be very, very low, getting very close to zero. Whereas anomaly data points are less, so the model will be having less exposure to this anomaly data point. So for these data points, it will not get minimized. Okay. Now, in that case, what will happen? So now we will be having, let's say, 99 data points with respect to normal category and 1% anomaly. In that case, the mean squared error for these data points will be very low. And if I take average of that, so they are saying that average of mean squared error for those data points, normal category is 0.004 because model has seen more these data points. Now, at the same time, for abnormal data points, the mean squared error is slightly more. It's not slightly, very high, right? So almost 10 times, 10 to 15 times more compared to your normal data points mean squared error. So from this, it is clear that I can identify whether the point is normal or abnormal just by looking at their mean squared error, right? But question is, what should be the threshold? So average value for the mean squared error, right? But what should be the threshold that will tell that above that we'll call it as a normal and below that we'll call it as a abnormal, right? So how to determine this threshold? So they have mentioned a couple of ways to determine the threshold using the one is logic is they have mentioned using the true positive and false positive rate using this formula, or simply you can take a mean value of the reconstruction loss, standard deviation of that, and using reconstruction mean plus 5 into standard deviation of that, that will be your threshold, right? And once you get the threshold, simply the logic is if the reconstruction score is greater than threshold, we will call it as a 1, right? Because if it is true, then it is going to return 1. If it is not, it is going to return false, right? So likewise, we'll get the predicted levels. And if you plot the confusion matrix, so it looks like this. Okay, so that means most of the points are correctly classified. Okay. Result at individual levels may bit vary, sir. Could you please elaborate, maybe if it is allowed for you to, open the mic and ask? The question is here. Okay, you question below this particular. Okay, and then stop this task and let's move to the final task, that is using GAN network. If you're getting different result, but hopefully they're not something different than achieving. Okay, but most likely you are supposed to get, perhaps you might have changed the percentage anomaly over 0.05. In that case, the results might slightly different, but ultimately, are you able to see the number of data points in that diagonal? Diagonally will be more compared to non-diagonal. So most of the data points are getting correctly classified. If it is so, then it is okay. But if your confusion matrix is showing many misclassified points, then something is wrong. But if it is maximum data points are correctly classified, so don't worry. It is possible that you may get slightly different. So go and try to launch the third chapter. Okay. question is how we use generative adversarial networks for solving the same problem. Again, we have a, generator and we have discriminator, right? So we know that generator's job is to generate the samples. They slightly follow the pattern of real data, that is from the training set. And the job of discriminator is to tell whether the data is coming from real end or fake end. Okay. Now question is how we can use this for the purpose of anomaly detection. And idea is very simple. So what we'll do, we will take all the normal data points, right? And we will train this GAN on the normal data points that we have in our data set. Now, if you feed all the normal data points here in the real set, we'll remove all the abnormal data points and we'll place it here in the real data. Now, if I train this generative adversarial network, so what it will learn? Your generator will gradually learn how to generate the samples. Those are normal, right? Because only normal data points are here. And accordingly, it will give you probability of normal data points as 1, right? So discriminator knows only how the normal data points looks like. Okay. So now in this case, you see, I have never used the labels here. So it is unsupervised model. And I just fed all the normal data points. So your generator learned that how the normal data point looks like. And the discriminator is trained. What's the difference between these normal data points and these fake data points? But once model is getting trained, so discriminator has only the experience of normal data points, most of the, right? And now what I can do, I can use this discriminator, right, to perform the task, whether it is real or fake. Not only that, I can pass this model where generator generate this fake samples. Now, if anomaly detection you have to carry out, so if normal data point is fed, then it will tell it as a normal because discriminator knows how normal data point looks like. But the discriminator has never seen the abnormal data points, right? So in that case, discriminator will give a lowest probability, right? Because for points, the probability will be 0.5, and for 5. So as simple as that. We're going to modify so we are not our model architecture again. We are going to just feed the normal data points to our model, and our model will learn how to classify your normal and fake data points using that discriminator, and generator will learn how to generate new data points. They are going to be again normal, right? So if I now finally I'll take 5 plus normal data points, so its probability will be always high. So discriminator knows how normal data points look like. But whenever I'm going to pass any abnormal data point, so its probability will be low, and it is going to tell that, okay, it doesn't sound like normal data points, right? So its probability will be less than 0.5. And then if the probability is falling that threshold, we are just going to say just it is going to be abnormal data point or anomaly. That's it. Okay. And that is what we are going to do in this third chapter. Right? So nothing very fancy work here in case of GAN. We are going to just use it as it is on the normal data points, and we'll use discriminator for the identification of anomaly. Okay. So again, the details I'm not going to explain it here because we have explored and we have invested 2 hours on the understanding GAN network. So again, some pre-processing is happening. So this is a binary labeling, right? And this is just a number of data points we have. Normal data point test. So we're using only the normal data points now. X10 is having the all the normal data points, right? So 7,29,000 normal data points are there. So we will use them and we will try to train this generative adversarial network, right? So again, the theory of that is mentioned here. So generator is defined here. So input dimension is 114. That is your number of features you have. Then gradually we are adding number of neurons in the subsequent layers 128, 256, 256. But output layer of generator is going to be again here 114, right? Because that is the number of features we have in our input data set. Okay. Likewise, we will also construct the discriminator here, right? And output layer is going to have only one data point, one neuron here, right? And activation function is going to be sigmoid, right? Again, for discriminator, input data size is 114, and remaining layers are again you can modify as per your requirement, right? But as of now, don't modify it. They have tested and it is working fine for this particular architecture. So we will construct this neural network now. We'll set some hyperparameters like learning rate, batch size, number of epochs, etc. And we'll train this model on normal data points. Okay. And it will take few minutes to train this model because a slightly heavy model we have now compared to the autoencoder. So it may take 5 minutes. And after that, we will see the training loss and anomaly detection is going to be simple, right? So as I mentioned, if it is crossing that value 0.5, then it is labeled as 1 normal and 0 for anomalies less than 0.5. Okay, fine. So let's and you can also go and try to understand these parameters and the network and then execute, and let's wait for this model to get trained. Okay, so model is trained now, and if you see the loss, you can see some hiccups were there, but again it is saturated and it is stable now after these. For the anomaly detection, will be using that threshold, that is we are going to use 1% of the test set comprised of anomalies, right? So we will just use that if that value is greater than 1%, then it is normal, otherwise abnormal, right? And with that logic, you can see the F1 score, the accuracy, precision, recall is also around 94, 95%, and accuracy of 99%. And if you verify the confusion matrix, you can see only 250 around points are misclassified and most of the points are correctly classified, right? So that is only takeaway from this notebook, that how we can use the GANs for anomaly detection, right? So to summarize, we have used these unsupervised models. The reason is it is not always the case where you will be having attacks or pattern of attack that has happened in the past. Okay, so they're going to, the attackers are going to innovate new ways to attack or breach the system. Yes, right. You need a model which is going to be normal. Something is wrong with this particular attack, and you need to verify it. It will get classified as anomaly. Okay, so this is about GAN, how to use it, and this is where we will conclude all these 3 chapters, right? So you can stop this chapter task and you can attempt for the assessment. And for the assessment also, again, you have to start this instance. Okay, so I will
Sir, lost your,
fill some codes. Yes. Yes, Abhinav.
so we lost your voice in between.
Okay, is it audible now? Hello.
Yes, sir.
I think we are, your voice is also breaking for me.
Okay.
Rest of the participants,
Okay.
is it for Abhinav or for all of you?
We can hear you well, sir.
Okay. So now the final assessment where you have to start the instance. Okay. It will take a bit more time. show you that this course. Okay, sorry, I think there was an issue from my end of the network. So here I think on this repo you'll be able to see the assessment notebook also. Okay, so again a similar data set you'll be working on. So what you have to do again, they have used uh, this particular import first of all TensorFlow and the scikit-learn. Then again the loading of the data is same as like in the previous case. We'll be having these labels. You will see slightly different data set with the normal data points around 13,000 and abnormal around 12,000. So it is slightly balanced data set now. Then pre-processing again similar they are going to do. Okay, I'll not go into the details now. And now, for example, there is a task for you, data selection, and there will be some fix me parts in your code that you have to modify, right? So for example, I think they have mentioned fix me here at this point where you have to specify what should be the test size. So let's say here we consider 20%. And I think here also they have mentioned fix me where you have to just mention the labels that we have loaded. So it will this label encoder is going to convert these labels into integer labels. Okay, that is one thing you have to fix, and that is was already there in the first chapter. Okay, so likewise you will get then the second chapter assessment task. They're asking you to set the XGBoost parameters, and some fix me will be there here. The same parameters that we used in the first chapter of this course that will be mentioned. Then here you have to mention GPU hist. It is going to be multi-class classification, so multi-soft probability you have to mention, right? Then for model training, they might have asked you to mention these labels here. Okay, and likewise only the fix me part you have to take care, right? If required, you can refer this notebook. I'll share it with you, right? If you stuck at any point, you can have a reference for that, and you will be able to complete, right? And again, the procedure remains same. So once you go to this end of this chapter, right? So their task, your goal is to achieve at least, I think 95% accuracy, right? For XGBoost, right? And for 90% at least for the autoencoder. So these two accuracies you have to achieve. Okay, at least 95% for autoencoder and 90% for autoencoder, XGBoost 95%. And once you get, you'll get this congratulation message. And then once you do that, I think there will be assess task here, but if not appearing, then I think that is the only thing you have to do. And you have to make sure that you are going to attempt for this MCQs also, right? And once you do that, automatically you can see on your my learning section certificate will be appearing in this certificate section. Okay, so fine. So you can attempt for that, right? Yes, finally you have to click on assess task also once you complete that assessment task. Okay, so in case you are facing any errors, so there could be the issue that somewhere you have not updated your code properly or some values are not as expected. So you have to experiment for different values. And again, you have to execute from beginning. So for this particular notebook, typically participant make mistake like they are going to, modify some, let's say cell here, let's say instead of 20%, they mentioned 30%. So in that case, maybe also accuracy is going to vary, right? Likewise, somewhere here they have mentioned number of round, let's say only 5, then the maximum depth equal to, let's say 2 only. So likewise, if you change these parameters, it is going to affect the accuracy. So I encourage you to maybe you try it for yourself for different, values for these and observe the accuracy, how it is going to affect. Obviously, you cannot change this number of class because it is going to be constant, but learning rate, number of rounds, maximum depth, that those parameters you can, play around, and you can observe this accuracy at the end, right? So if you stuck at any point, so I have shared the link with you. You can, verify, right? But typically, you are expected to see accuracy for XGBoost 95% at least, and 90% for autoencoder. So go through that, solve these assessment, and finally click on assess task once you get the successful message. Okay, fine. So complete this certification also. And as I mentioned, very soon we are going to share one drive link for you to upload your certificates. And based on your certificate submission, we are going to finalize the participants who can qualify for the refund. Okay, fine. So now we'll conclude here. If you have any question related to this, you can ask. We have still 5 minutes to spare. Otherwise, we'll conclude here.